Being an engineering student means to spend a lot of time studying, a lot of time learning, a lot of time working on cool projects all night long. But then, after all the sleepless night, something happens. An idea. I realize that I can use all the knowledge that I'm gaining to create something unique, something to be proud of. But I need a partner to build my new amazing startup, so I decide to share my idea with my closest friend. We are really excited about it. However, it begins an exhausting list of expenses needed to launch a startup. A website domain, more cloud storage, even a designer to make a logo. I can't afford all these expenses, but I can find a solution to the last problem. Of course, I'm not a designer, I'm an engineer, but I can use my skills also to create some fancy logos. As always, I need only two things, my laptop and math. Let's start from the beginning. The idea is to create a stylized logo, starting from a picture. The core of the project is a class called Fourier Sketcher, with these properties. To create an instance of this class, the file name of the original picture is needed, together with a threshold for an high-pass filter, one for a low-pass filter, and another for an intensity selection. These parameters are the main responsible for the final result, and must be tuned properly. The pre-processing is based on four main points. Firstly, the original picture is converted to a black and white image. Then, an high-pass filter is applied, multiplying the picture discrete Fourier transform to the Fourier transform of the filter. After that, the inverse fast Fourier transform is applied to obtain an image with the border of the desired figure highlighted. Lastly, the coordinates of the pixel with an intensity above the specified threshold are stored. Then, the more artistic part comes. A low-pass filter is applied to the stored coordinates thanks to the discrete Fourier transform. And in the end, applying the inverse fast Fourier transform, we obtain the desired picture. Lowering the threshold of the low-pass filter, we obtain more stylized pictures. This method requires high contrast pictures and a tuning of the input parameters, but the results are quite nice.
Stop! If you don't want to miss your package when listening to music, you should use our app. Let's rewind and see what happens. This program can be used with any type of doorbell and will notify you when it rings, even when you are not listening. We are not responsible for any damages to personal properties while using this program.
Welcome to the Signals and Systems project of Group 42. Our project goal was to recognize a doorbell sound from a background noise. This is to solve the issue that when you are listening to music, you might miss the doorbell ringing. Our code will listen to the doorbell and notify you when it rings, so you can listen to your favorite music. We will start at looking at the setup. First, the code needs to know what our doorbell sounds like. This is done by first recording 5 seconds of audio in which the doorbell needs to be played. This gives some audio data. In case of our doorbell, the data looks something like this. But with this data we can't do nothing yet. We first have to apply a fast Fourier transform to it. This will give, for each frequency, the amplitude. Our audio data looks then something like this. These 2 large spikes are characteristic for our doorbell sound and needs to be stored in a variable. We chose to store the 4 largest amplitudes, since there are multiple peaks inside the 2 large peaks. Now we ensure that we at least have 1 frequency for each peak. With these amplitudes, the row data and the frequency data for these peaks is determined. Now we know what our bell sounds like, so we can continue to the recognizing phase. The recognizing phase has made use of a for loop. Each step of the for loop, a 5 seconds audio interval is recorded. Because the bell can sound between those intervals, the previous interval is also stored and combined with the new data. The code will look at both intervals at the same time. This is done by applying again a fast Fourier transfer to the data. This again gives the amplitudes for each frequency. Each amplitude of the 4 determined frequencies is compared to a barrier value. The height of the barrier value can be changed with the value sensitivity. If the amplitude of the 4 frequencies is at least half as high as the original sound, the code recognizes a bell. When the code recognizes a bell, image of a bell is shown and the bell is played.
Hello and welcome to the video of Project Group 99. Since there are so many applications of the Fourier transform, we try to do something fun with it. So, when we take a signal that we like, music for example, and a device that's interesting for a mechanical engineer, a 3D printer, and we combine those 2 things, what do we get? Exactly, 3D printed Jukebox. For the 3D printer to play the music, a code is needed. Since the printer we use has 2 motors capable of producing high frequency sounds, we decided to play the 2 most dominant frequencies for the music selected. We got to these frequencies by the following MATLAB.
I'm going to talk about the code, what it does, and why it does these things. The goal of the code is to convert any audio signal, preferably music, into a G-code which can be read by a 3D printer so that it plays it using the motors. Let's start at the beginning of the code. Here, the audio file can be inserted, and the duration says how much of this audio file you want to really hear. The T-step determines how big the intervals are over which the dominant tones will be selected later on. In the pre-processing, the file is actually loaded and an interesting bandpass is placed. This bandpass is necessary to make the sound a little bit more pleasurable to listen to. Often, there are some high tones which are not crucial to recognize the sound or song and not so nice to hear. This bandpass fixes some of these issues, but it needs to be altered for every song that is put in. In the for loop, the actual Fourier transform comes into play. The sound is transformed for every T-step. The maximum value is taken, which represents the tone with the most volume. This is then saved. The second maximum value is taken, but since it is the same as the first maximum, it is deleted, and now a third maximum can be taken. Now we have selected 2 tones with the highest volumes for every T-step interval. These are saved and transferred to frequencies for which data points are generated to replicate the sound waves using a sine. We have now made an entire sound signal which consists of an array of frequencies which change over time. In the next part, the data points can just be saved and played on a computer to see whether the sound is somewhat correct. This was used for testing. Then finally, all this is converted into data that the 3D printer can understand. The frequency depends on the speed that the motor travels. Some if statements are necessary to make sure that the printer stays within the boundaries that it can actually travel. A .txt file is generated and saved, which can be copied directly into the G-code, and now you can play the music on the 3D printer.
We're Group 30, and this is our Signals project. In this video, we'll explain our concept and how we managed to implement it in MATLAB. Our aim was to visualize music using MATLAB. In this video, we'll explain how we did that to create the moving graphics that you can see on screen. We wanted to visualize the audio by looking at it in the frequency domain. In order to do this, we take the Fourier transform during a small time frame window and plot it. These plots are histograms and are amplitude normalized. Then, we move on to the next time window and repeat this process. Doing this manually would take a very long time, so we automated the entire process using a for loop. We take a certain amount of frames per second and then chain these together to create a video file.
The code we made works as follows. The code takes two input arguments, a music file and a number of frames per second. With these inputs, the code can create a visualization of any audio signal, as you might have seen at the start of this video. The code works by first reading the audio using the audio read function. Next, we create a for loop that for every loop takes the Fourier transform of a small segment of the audio. This Fourier transform is normalized and turned into a bin plot. These plots are turned into frames and put in a sequence by the video writer object. This video is output to the MATLAB directory.
Last night all I think about is you. Don't stop, baby, you come up too. Don't want, baby, think about you. You know that I'm never gonna lose.
This was our project, thank you for watching. We want to give a big shout out to Innovation Security for not kicking us out and letting us stay until the deadline. Also thanks to our parents for paying our tuition so we can do this. Big thanks to our teacher Duarte too. This has been Group 20 signing out.
Group 30, bruh.
30. Fuck's sake, I misread.
How's the video going?
I think good. I'm gonna kill you, bro.
Welcome to my presentation for the Signals and Systems course about the Fourier transform. Using the Fourier transform, you can transform signals.
Ho. I cannot understand this at all. This is garbage. You get a 1.
Do you recognize this problem? Have you seen this happen to someone else? Maybe a relative or a friend? We have the solution for you. It's called the Anti-Lispinator. For just a mere price of €159.99, you can get one yourself. So, here we will show you the amazing code of the Anti-Lispinator. It will start off first with loading up the audio files, as you can see over here. You can then take a look at the signal by using the amazing discrete Fourier transform of the audio. Below you can even see the plot of the discrete Fourier transform. Now it's time to filter the data that we computed before.
we want to filter out the lisp, which is the sound of the S that can be found during lisping. We do this by using a filter that implies that high frequencies are filtered out of the audio file, leaving only the low frequencies behind.
It's amazing!
After this, we're going to do the same, but with high frequencies. In order to not lose the complete sound, we will pitch them down and therefore making the S sound less evident. To make the desired sound, we will finally combine both audio files in one file in order to give the desired output of the Lispinator. The result will now be shown on one of our recent happy customers.
Welcome to my presentation for the Signals and Systems course about the Fourier transform. Using the Fourier transform you can transform signals and...
Yes, very well. You understand the Fourier transform very good. You get a 10.
Disclaimer, price does not include tax and import fees. That not guaranteed. Happiness not guaranteed. Product does not include the beautiful actors.
Lock the door.
Voice authorized. Door locked.
Open door.
Voice unauthorized. Access denied.
Damn it! Ella, I need you.
What's the problem?
The door is locked with voice recognition software. Can you transform my voice so it sounds like Bart's voice? Because then I can open the door.
I'll start on it right now. What do you think the code is?
I think the code is open door.
So, what I did.
First we open two audio files of the voices and use only the first column. Then we look for the amount of samples in the fragments and find what frequencies are in the audios. Next, both audios are Fourier transformed and the medians of both transformations are found. From the medians, the indices are computed, and based on that we can pick the right one, since it has to be positive. Then we can fill in the index in the frequency domain to get the frequencies of both audios. Lastly, we scale the different frequencies to get a scalar. For the next part, we open the audio of what we actually want to transform and take the first column again. We set up the needed variables and carry the signal using the Hemingway technique. This makes sure that the voice doesn't become too robotic. A scalar is used to make it normalized. Next, a number of iterations is set. Take 10 to get the best results over calculating time. Then, make an empty matrix and start at step 1 and loop over the amount of frames. Use the Hemingway transform and then resample. Use a Fourier transform to make the first result and loop over the number of iterations. By calculating the angle of the result, we know if we should move to the left or to the right. Lastly, make an audio signal using the reverse Fourier transform and rewrite the result. Add everything to what we have so far, increase the step size, and write the file.
Thank you so much, Ella. I got it. I will try it right now.
Open door.
Voice authorized. Access granted.
It worked. I'm in.
Huh? Why is the door open?
It's been 10 years since they went missing. Every day I think about their case, what I could have done to find them, what I could have done to be better. But now, it might be too late. Who knows what they look like now? They were just children. After all this time, they're no longer that, if they're even still alive. I spent countless hours looking at suspects from family to strangers, with no avail. It's driving me crazy, taking over everything. If only we could figure out what they'd look like now. It would make everything so much easier. But I don't know how.
I got it.
We got it. This is what they look like.
But how?
It's all here.
The IM read lines convert the images to matrix form. Then we take the mean of these matrices in the third dimension, and the double function is there to ensure that MATLAB is using numbers that it can process quickly. Then we begin to apply the low-pass filter. So first we set the width of the Gaussian, then we create two matrices using the z-score going from 1 until the size of the image in the first and in the second dimension, respectively. We make the Gaussian filter, and now for the Fourier transform. Since the fast Fourier transform goes from 0 to fs, the FFT shift function makes it go from negative fs over 2 to fs over 2. Now we turn it all back to time domain, but before we can do that, we first have to apply the low-pass filter. This means that we multiply by the Gaussian to ensure that all the high frequencies are essentially gone, and then we shift back to an FFT style, meaning that we go now from 0 to fs by using the IFFT shift function. Then the IFFT function inverses the fast Fourier transform that we did before. We take the real numbers of this and we store it under a variable called imgfather. For the high pass filter, we do the same thing that we did for the low pass filter, but for the Gaussian, we do a 1 minus the rest of the equation, because we need to filter out the lower frequencies to get the higher frequencies by themselves. The same process for the low pass filter is done from here on out. So to wrap it up, we resize the images so that they get a better fit, and then we use the IM fuse to blend the pictures together. And this gives us the predicted baby.
After all these years, we can finally solve this case.
Breaking news from the BWPD. Detectives have solved a 15-year-old unsolved missing persons case involving two children that have since grown up using breaking technology that makes the composite images using their parents' faces. Using this technology, they've also managed to identify other
missing children who all seem to have been victims of the same serial kidnapper, who police have not yet managed to identify.
Hello everyone. In today's video, or project video, I will be showcasing a project I worked on regarding signal processing for my Signals and Systems course. The aim of this project was to showcase the usefulness of Fourier transform. As most people think of sounds when thinking about signal transforming, I thought, let's flip it upside down and do images. I have a large collection of images laying around that I wish to be digitalized for safekeeping for future generations to see. Sadly, most of these images of my grandparents have silly little perforation marks that probably got introduced during the processing of these images. Luckily for me, the Fourier transform is a perfect way to remove these blemishes. As when the data is fast 2D Fourier transformed, the image is shown in a totally different way, with a bunch of spikes. These spikes contain information. The central spike contains most of the information of the image, and as such should be left alone. The farther away we get, the less important and more blurry information is. In this 2D Fourier plane, we can see its peaks. These peaks translate to patterning visible in the image. The more visible and regular the patterning, the better visible these peaks are. The central peak contains most of the important data and should generally be avoided. For this, I wrote a 10% grace box around the center. This should keep most of the generally important data away from the hands of the machine, which is looking for a predefined brightness threshold in the image. Each image has a different threshold for filtering. Being able to choose this is important, as if you filter out too much, the image becomes a big blurry mess. The code was made with general usage in mind. As such, file selection, saving and prompts are put in to showcase what it does. As of now, the implementation is only there for grayscale images, and the code will grayscale your images for you if they were not grayscaled before. Don't feel afraid to use any other image than the ones I showcase here to test out the code. Be sure to change the threshold. Usually a value between 9 and 12 is where I find it to be most useful at. Now I will showcase a couple of the examples I've made. Thanks for watching this video, and if you have any questions regarding anything, feel free to ask away.
Wind is the fuel to our minds. We long for connection with the elements. That's why we decided to turn wind into art. But how did we do it?
Using wind speed, wind direction,
wind north at 12 miles an hour,
and wind gusts, Fourier transforms,
2 hours later,
and other data analysis tools, the images can be created. Wait, first a loop has to be created. With this loop we are easily able to store the Fourier transform data for every single day in the dataset. This will make it easier to store a lot of data values. Once these values have been normalized, scaled, and converted into integers and RGB values, they can be placed in a RGB value to color converter. The created image can be incorporated in and on products that wind lovers may use, such as kites, boards, or sails, in order for them to feel more connected with the wind and nature. As can be seen here, the new design looks much sicker, and allows the kiter to successfully land.
In your whole story, right? So you can use MATLAB Python, or if you want any other language, okay?
Wait a minute. Have you guys also realized that this lecturer sometimes says okay? Well, he says it a lot of times, but it's usually after something very important. Just look at this next example.
And there's friction, if it's described by a linear, and I said it is linear, but also time-varying system, so indoors, you can still use convolution to predict the trajectory of where the ball is going to be at.
Okay, those were probably enough examples. But what if we could create a program which finds all the different OKs in the lecture and then timestamps them for us? This would mean that we would have all the important information in one hand. We could then easily create summaries, etc. and study for the exam. Well, we made this program. And in this next clip, we're going to show you how we did it.
Let's get into the code. First, we have cut a little audio file of one of the lectures, which contains OK. Then we have cut this file even smaller to only have the OK remaining. This will function as our reference file. This file will be compared to the other parts of the lecture to find the OK. To make the spectrogram, we are using the spectrogram function in line 36. This spectrogram function makes use of short-time Fourier transform, so most of the work is done there for us, which is nice. To run this function, we define the number of samples, which we calculate by multiplying the length of the reference audio and then multiplying it with 20 milliseconds, because this is recommended for speech recognition. Then we take a window using the Han function. This is to prevent discontinuity. And then we define the overlap to be 50%. We run the spectrogram function, and then we only look at 0 until 10 Hertz instead of 0 until 20, because we noticed that between 10 and 20 there was not much left of the voice. To use this image in our image processing algorithm, we disable the color bar and the X and Y axis. So then this leaves us with this image, which is the spectrogram of the reference audio. Now we're gonna load an unknown lecture audio into MATLAB. And also in this part, the lecturer says okay. Now the interesting part happens. We define some parameters for the for loop. And then here, we do the cool stuff. We are taking a window of the lecture audio we loaded in here. Then we are turning this into a spectrogram. Again, taking the Y limits, removing the power and the X and Y axis. And then we are using the SSIM algorithm, which is a structural similarity index, to compare and give a score of how similar our OK is to that part of the lecture. Then we do this a lot of times, which is also pretty hard for the computer. So on some laptops this will run in a couple minutes, while on the Lenovo of the 2022 first year class laptop, this will take about 30 minutes. When it's done doing this, it has created the file SSE, which contains all of the scores. If you say 30 minutes is too long, my laptop isn't that good, you can just uncomment this line of code, and then the file which is created by this code over here will be loaded in. Here we take the max score, and then we just put it in a nice graph, and then this will show you exactly that at 5 seconds plus minus the lecturer said okay. As an added bonus, because we're not done yet, we decided that okay, you have now a summary of what you when the lecturer says something important. But what if the lecturer is doesn't really like that he says okay this much? Maybe he thinks he says it's too much. It's too much okay. Well, to solve this, next to marking where the okay is, we can also take the okay out of the audio file. So this part of the code is a little bonus for the lecturer. We only use one reference, and that's to learn more about voice recognition and how to implement this. And then the possible improvements for our code are multi-threading, because this code only runs on one core, and because it's so computationally heavy, it will take a very long time on the bad computer. And multi-threading could improve this tremendously. And then lastly, we could add intelligence. So, for example, if the OK deviates too much, so if the score is too low, then it won't detect the OK. And now the system can only detect the OK that seems the most like the OK we used for our code. So if there's two OKs in the lecture audio, it will only recognize one OK.
Now that you've seen the code, I want to end this video with an example. I want to show what you can actually do with this program. Firstly, I'm going to show you a random portion of a lecture. This is unfiltered. And then I'm going to show you the filtered version of this portion.
Discussing the material in a way that assumes that you have seen those videos. Okay? So the videos, I think, discussing the material in a way that assumes that you have seen those videos. So the videos, I think,